Hi there, I'm Mihail Galkin. I'm a researcher in TU Dresden Fraunhofer IAIS, and I will be speaking about complex question answering over knowledge graphs. And in this presentation, we'll be speaking about knowledge graphs, some observations, and we'll be speaking about these systems depending on graphs, large KGs and smaller ones. I work for Fraunhofer Institute. We develop voice solutions, like, for example, industrial solutions, industrial speech and speech assistance platforms. We operate with knowledge graphs that are made of the triplets. Like, for example, we have this triplet. Wikidata is a knowledge graph, and by adding more triplets to the graph, we work with more facts. And we are speaking about the Wikidata. We are talking about Google, which is different from the concept of knowledge graphs, etc., etc. In this presentation, we'll be very often referring to Wikidata graph, which is the biggest knowledge graph which currently exists. More than 90 million plus entities and lots of nodes. And I think this is what makes it very interesting. As question answering goes, machine reading comprehension comes in first. When we work with a text document and we use some parts of this text as an answer. And the second one is the knowledge graph-based question answering, where we try to come up with a request in a kind of a language, some kind of a language, and come up with the answer. And these questions can be simple and more difficult. In the course of this presentation, I know that you expect that simple questions are pretty much solved. Simple questions are the ones that use and utilize just one single hop in our knowledge graphs. For example, Albert Einstein was educated at where? Just one single hop can provide you a quality reply with 95–97% quality, which is good. But instead, we'll be speaking about complex knowledge graphs queries where we'll be using more than one hop. Like, for example, theory of relativity author. Who is the author? Albert Einstein. That's the first hop. And then where was he educated at? It's a complex or multi-hop query, and it's the first tier query. The systems which answer complex questions sometimes depend on the size of the graphs. If it's more than 1 million triplets, then we have a certain number of systems which run some graph DBMS, and we can use some machine learning algorithms in there. If you have a smaller one, less than 1 million triplets, it's using in-memory neural reasoning and graph embedding, which we'll be talking later. So let's right now talk about large knowledge graphs, and they have two big algorithms. So we'll start with the templates, which operate at big graphs. Like, for example, if it's a template-based question and answer, part of this query matches with some of the template parts. I'm going to show you a few examples. Like here, for example, how many entity did entity star in? And we have already a template of the question which should be filled with entities, variables. How many films did Leonardo DiCaprio star in? So these are the entities filled in the question. With the help of our DBMS, we come up with the answer. So what are the pros? Of course, scalability. We can run quite a lot of queries in parallel and quite quickly and explain the results. And the cons really are as manual supports. For example, if you have more than 100 templates, provide support for them becomes difficult. And if you have these queries related to anthology and the words are changed, you'll have to change all of the templates, which gets very complicated. The second thing is multi-part parsing. So, for example, when we build these questions, when we come up with these questions, and they are made of 4 big parts.
We do entity linking, relation extraction, and we have a couple of representatives of this family. One of them is known as a QAMP pipeline. We launch those modules. Looking at our question, we select a subgraph. This is going to be a 2-hop subgraph, and then we arrange the query. We have a fast retrieval index HDT. And what else is exciting is that those queries are processed quite fast, less than half a second, which is quite fast. And our classifiers are rather simple. We don't have any heavyweight machine learning. Now, the second system that is using parts of queries that we call core chains. Depending on the direction, we create queries, and the quality turns out to be even higher if you use a complex data set. The quality is quite high. If you're looking for pros, some supervised machine learning can be applied. We can still explain the results because the query is quite often simple. We can also name some cons. We can say that the connection is a very sensitive area. If something is wrong, then we are going to have a problem. Although the algorithms are quite simple, this is close to brute force. We can use template-based QAs, and it's easy to play around with this. Second part, small graphs. Why we need this? When we make a query, it goes in a structured way, and we often see that the data sets in databases are not complete. Many facts are missing. However, many facts can be forecasted. If we do the in-memory reasoning, we can forecast new links. That is going to provide fairly good quality, and we would be able to come up with very accurate results. This is a multi-hop reasoning example. We can use scoring algorithms that we use in other systems. Instead of triplet ranging, we look at the number of candidates. We upload all entities. within 2 hops from the initial one. The most complex situations would include 2 or 3 hops. What we see here is that the quality ends up to be quite high. Even with 3 hops, we see 90+%, and that is very good. We believe that the quality improves over time. This is really a state-of-the-art system. The graphs may be quite small, a small number of graphs. If they grow bigger, then you would need a lot more GPUs. And then the outcomes would not be as great. Finally, let us talk about the latest family. That is query to box. The idea is to use hyper rectangle boxes. We can use those hyper boxes to work with EPFOs, and this is what happens with d-dimensional boxes, where you have essentially 3 operations: projection, intersection, and there's a distance. Every entity is a hyperbox, and we can use combination of those boxes to model various logical formula. We can model an intersection of this type. However, there are some issues. If you want to simulate, then you need to have a big space. So there is a way around it. You can convert all queries to the DNF union as the last step, and then you are going to get an answer. The system has proven itself quite good on the unseen conjunctive queries. Then we do the testing using unions and intersections, and surprisingly, the system works quite well. The bad thing is that you cannot use it with big knowledge graphs yet. You don't need no database, no query engine. You can use incomplete KGs, infer new facts, and you can predict links. The disadvantages is that it's hardly scalable to large graphs and often not explainable in terms of results. It's also computationally expensive, and we cannot handle literals. This problem is still there. However, this area is growing very fast. We see several papers at every conference that we have on this subject. There are several challenges that we see. One of them is answer verbalization. When you have a graph that answers the question, it's always nice to have a verbal answer. That is to say that Einstein learned in the University of Zurich and in ETH Zurich. This task, though, is quite complex. However, there are generative models that can be used to address this. The second challenge is hyper-relational knowledge graphs. There are additional key values that we find in the triplets, and they turn into statements. So we end up with extra attributes that we call qualifiers. They are very good to narrow up the search space, but there are not many systems that can use those qualifiers today. And the last challenge has to do with immediate answers to questions in dialogue environment, when we have to understand that the next question is going to be put in the context of the previous question, and that imposes certain constraints on our graphs. Like in the next column here on Led Zeppelin, how many albums they had. Then there are other questions in the same context. What was the first single released in one of the albums? And there are one or two data sets to look at. Every year we see a number of new research works on this subject. That's all I have. Thank you very much for your attention. You can see my credentials. You can reach me if you want. I will be happy to take your questions. Thank you very much, Mihail. I have the following question for you. You told us about an area that is between NLP and the maths that stands behind the knowledge graphs. There are large transformer models out there. They've become so successful because we have transformers. As of the graphs, the leap has been made already. There are new types of layers that would allow people to make the same leap in the field of graphs. Well, we have not had that leap yet. The graphs are very different in different domains. There are three big tasks: node classification, forecasting links, and graphs may have different geometry, different topology. Therefore, there are different layers in graph networks. They publish many of them all the time, and it's difficult to find something versatile. There has been some publications about the pre-training of graph networks, but at this point in time, they only do evaluation with simple tasks. And then again, if there is a typified or multi-relational graph, that is going to be a different story. I thank you very much for this very interesting, very exciting presentation. It was very cool indeed. Thank you.